All right, let's jump in. Thank you all for joining. Good morning, good afternoon, everybody, and welcome to the BPI webinar on PHA, from raw materials to products, PHA and how it's used in certified compostable products. On behalf of myself and BPI, we're very excited to be here with you and very grateful to our presenters for donating their time to increase education around this important topic. Thank you to Leah Ford with CJ Biomaterials, Anthony Keys with Nature Tech, and Michael Adams with WinCup. My name is Jorge Montezuma. I'm principal consultant for One Organics, a consulting firm working to expand composting infrastructure across the country, and I work for BPI on various composting related projects, including the Composter Municipality Committee and the previous series of webinars navigating the life cycle of certified compostable products. We are recording this webinar and it will be available on the BPI website at a later date, as well as on the YouTube channel. We encourage everybody to ask questions using the chat box, the Q&A chat box, rather than the regular chat box. And we encourage everybody to stick around for that portion as well, which won't be shared in full. So it's typically a very exciting part. Want to remind everybody that BPI has published a 7-part webinar series that run last year. We wrapped up earlier this year, and we followed the journey of certified compostable food service packaging. We heard from 21 expert practitioners, starting with composters, collection program managers, professionals involved in certification and testing, as well as biomaterials experts. And since there are more topics to explore, we decided to host another webinar on PHA, and this is where we are today. So before we get started, I'm going to hand it off to the BPI Marketing and Communications Director, Leslie Rogers, to tell us more about BPI.
Thank you so much, Jorge. And please let me echo our appreciation for our presenters today. And thank you for joining us. I can't wait to see this content. A little bit about BPI. So we were founded in 1999, and BPI is the leading authority on compostable products and packaging. We're a 501c6 membership-based organization of stakeholders with a vision. Our vision is a world without organic waste. We do this through our mission. We support the shift to a circular bioeconomy by advancing policy, standards, research, and science-based verification of compostability and biodegradability. We have 3 core objectives. The first is claims. We work to advance trusted and scientifically based standards, research, and claims. We support adoption to align and collaborate with stakeholders across the value chain to advance BPI's mission. And we work to influence policy, policy that supports a systems-based approach to products and materials. And Jorge, I will turn it over to you and our presenters. Thank you again for being here.
Thanks, Leslie. So I'm going to turn off my screen now and pass it off to Leah. And while she does that, I'll introduce her. She's a director of marketing for CJ Biomaterials, a leading manufacturer of PHA biopolymers under the brand name PHACT. Maybe she has a way to say that acronym that's different than saying each one of the letters. Previously, she held roles as digital marketing manager and global marketing and communications director. And throughout her career, she's seen the market evolve to enable new pathways for materials in the circular economy, like compostability, and to prioritize low carbon bio-based materials. She has a passion for working on sustainable materials, which stems from her background in earth sciences, where her research focused on landscape evolution and the impacts of climate change on landscape. She holds a BS in geology and a master's of science in geomorphology from MIT, and she currently serves on the BPI board. Very excited to have you join us here today, Leah. Off to you.
Yes. Thank you so much, Jorge. And it's called fact. Like
There we go.
PHA is just a fact of life, right? Or fun facts. We have many, many puns that we can use based on that brand name. So I'm happy to run through many of them today, which is great. So thank you so much to BPI for the opportunity to talk about PHAs, which is one of the newer, very cool biopolymers that we have out there to put into our design toolkit when we're designing food packaging and food serviceware for compostable applications. And so today, I know I'm going to start with some of the fundamentals around PHA, how CJ Biomaterials fits into that picture, and talk about what's possible with this new class of biopolymers. So let's start off with what PHAs are. PHAs are very cool. They have been around on the planet for millions of years, and they are one of the only, if not the only, common naturally occurring thermoplastic on the planet. And so PHAs, they are actually part of the normal metabolism of microbes, and they're found like on the table I'm sitting at, in my body, on our foods. You can find bacteria that can make PHAs just about anywhere. And what they do is when they consume sugars, oils, other types of foods, if you will, they turn that carbon into an energy storage. So the same way we eat food to be able to store energy in fats, bacteria are able to store energy in PHAs. And then we are able to use those PHAs as a thermoplastic to be able to create a wide variety of applications. And so I kind of have that spelled out here. And PHAs can begin with a feedstock that can be sugars, it can be plant oils. You can even do this via gas fermentation using things like carbon dioxide or methane. There are several ways that you can begin the fermentation process using bacteria to be able to create PHA. And that third circle there, that's really where the magic happens. It's very cool. So that's where you can actually see the granules of PHA developing inside the bacterial body. And once those have grown to maximum percentage, we're able to separate the cells from the PHA, purify that PHA, and turn it into plastic resin pellets that I think are pretty commonly viewed amongst our industry. And from there, we can turn that into a wide variety of packaging. So anything you can use a thermoplastic for, from paper coatings to injection molded cutlery to thermoforms and even nonwovens that you can use, for example, for in combination with cellulose for paper towels. You can make all of these things with PHAs. Now, PHAs are sometimes referred to as the next generation biopolymer because there's sort of a new wave of commercialization that's happening right now. Larger companies getting involved in manufacturing PHAs, and we have some new types of PHAs that are helping us create more functional products. But this is a polymer that's been around and identified for well over 100 years. So back in 1888, actually, PHA inside of a cell was first observed by a Dutch microbiologist, Martinus, and I apologize, I cannot say his last name. So we'll just call him Martinus. He was the one who first observed PHAs. But then Maurice Lemogine, who is French, was sort of considered the grandfather of PHAs because not only did he identify them in cells, but he was the first to really extract and characterize PHAs and document how and why they grow inside of bacterial cells. Fast forward a little bit, PHAs were actually commercialized and produced at a semi-commercial scale for the first time in the 80s. So coming off of a wave of the oil crisis in the 1970s and a lot of markets being concerned around the expense of petrochemicals, there was renewed interest in bio-based polymers. And PHAs were one of the ones that was being produced and looked at scale. And so that actually launched in the 80s under the brand name Biopol. And they were producing about 10 kilograms a week of the very first PHBs at the time. Then in the 90s, a company called Metabolics was founded out of some research that had been done at MIT that gradually becomes part of the CJ Biomaterials portfolio. But it was really in 2016 that CJ Cheiljedang acquired that Metabolics technology, and we've been bringing a new sense of scale and new types of PHAs to market. So it's been a long journey for PHA, but we're at a point where we've all seen the demand for biopolymers, compostable alternatives. We want solutions to plastic waste in the ocean, persistent microplastics, materials that are compostable, that we can trust. And it's brought a renewed sense of interest, R&D, and scale into the PHA space. Now, PHAs are not just one type of polymer. right? There are, depending on the composition of monomers and comonomers, well over 150 types of PHAs. There is a smaller segment that has been identified as, if you will, commercially viable as thermoplastic replacements for materials like polypropylene, polystyrene, and PET. And depending on how you vary your comonomers, you can get some very different properties out of PHAs, which is very cool. So we can produce PHAs that are, as you see here on the left, very crystalline, very brittle, maybe have a high melt temperature, to materials that are really amorphous. And one of the things that CJ was able to do is to create a very highly amorphous form of PHA, which is very rubbery and very soft, but also is an amazing bio-based modifier for semi-crystalline PHAs, as well as PLA, PBS, and the other biodegradable polymers. So we can tune throughout this whole spectrum, not only how fast maybe a polymer biodegrades, but also how flexible or crystalline it is, so that we can meet the needs of, let's say, paper coating versus something we're going to injection mold into cutlery. And as you can see here, PHAs are across the spectrum when it comes to everywhere you can use a thermoplastic, you can use PHA. We've got some very nice flexible films, rigid food packaging. You can injection mold it to make hot cup lids. PHAs naturally are very heat resistant, which is really nice for some of those hot applications. But of course, especially for compostability, it's really those food adjacent applications that PHA has a lot of applicability for. So PHAs are readily biodegradable, meaning the same microbes that can put it together can take it apart. And we are able to use those PHAs in combination with other biopolymers to tune not only the rate of compostability or biodegradability, but also tune performance properties in these materials. And what's particularly cool is, unlike recycling, where a monomaterial structure is valued to be able to preserve quality when you're recycling materials, in the compostable product space, as long as we meet the same criteria, for example, to get a certification through BPI, as long as we know we meet ecotoxicity, biodegradability, and disintegration timelines, we have a whole portfolio of materials that we can work with, and PHAs are a critical part of that portfolio. I noted before that CJ was able to produce a very amorphous form of PHA. This is an incredible additive, especially in combination with PLA, which has a lot of inherent stiffness and strength. But you can make films strong, yet very flexible and soft when you mix PLA and amorphous PHA. You can also increase the impact resistance in a PLA thermoform if you add in amorphous PHA. And so we're able to take advantage of this whole portfolio of biopolymers that have similar traits around end of life to create really functional multi-material structures. So that's something I think is very cool about the compostable product space. But why get into PHA manufacturing? And is this ready for scale? Is this ready, a material that's ready for replacing the large traditional plastics that we've relied on for the last 60 plus years? And so, because we know, and I'm not going to walk through this whole slide, but bringing a new material to commercialization and even a new application is incredibly difficult, right? It looks like, yes, we've launched this nice new product, but behind that, we've done a tremendous amount of work in benchmarking mechanical performance, making sure a new material like PHA can convert at scale, making sure we have food contact certification, we've passed our ecotoxicity testing, and really trying to bring all of these attributes together just so that we can launch a nice new product. And that's sort of where a company like CJ comes in. So CJ is a very large South Korean company that has a lot of different business units in food, entertainment, and logistics. But their bio division has long been focused on creating new materials through fermentation. And in fact, jumping a little fast, globally, CJ has over 700,000 tons of installed fermentation capacity. Because as I noted earlier, the key to PHA is in that fermentation step, feeding sugars to bacteria who grow that PHA. And so being able to do fermentation at scale is a critical attribute of being able to produce high quality PHAs and to produce them in quantities that are going to allow us to replace some of the traditional materials on the market. And so right now, for example, we're producing in Pasuruan, Indonesia, we have a 15 kTA plant there that can produce both semi-crystalline and amorphous PHAs. But we're looking at what's coming next. We know that the market for compostable products is growing and that PHAs have a unique place in diversifying the type of mechanical properties we can expect in compostable products. So how quickly can we get to scale? And when you have this much fermentation capacity installed globally, it's going to allow us to scale to be able to replace every straw on the planet with something that's very nice made from PHA very quickly, for example. And this is just sort of a summary view of all the types of processes and applications that just the product portfolio, for example, from a company like CJ can replace in or use for PHA. So, for example, PHAs are suitable for film, sheet, thermoform, spun bond, and melt blown nonwovens. We can create really nice compounds with materials like PLA or PBAT. And this year, what's new compared to the last 100 years is not only are we able to have this very amorphous form of PHA that is an amazing rubbery impact modifier, but we're starting to launch the first all what we call like the all PHA compounds. Because semi-crystalline PHAs have been on the market for a very long time, when we can combine all those different, 150 types of semi-crystalline PHAs with this new amorphous PHA, we're able to design new functional compounds for applications like paper coatings and cutlery have been two of our initial market targets. And it goes to show that, with so many different types of PHAs on a spectrum, we're able to really tune the types of properties we're looking for in product development. And of course, certifications are what underpin our ability to make trusted claims when we're using PHA. So PHAs typically have bio-based content certifications. They can be considered commercially and home compostable, as well as marine and soil biodegradable. We're very pleased that we have BPI's new commercial and home certification for our PHAs. And so this is enabling the supply chain below PHA manufacturing to be able to innovate and create more final products that meet both commercial and home composting conditions. And the certifications are really capturing like how for PHA, because it is made as part of the normal metabolism for bacteria, these are the same microbes that like I said earlier, they can take it apart, right? They're able to take the carbon that is in certified compostable products and convert that back into carbon dioxide. So these bacteria are found everywhere. They're found in the compost piles. And I know that Anthony, speaking after me, is going to go into this in a bit more detail, but it's really an interesting idea to have a material where the same microbes that put it together can take it apart. So with that, I'd love to turn it over to Anthony next, I believe.
Thanks so much, Leah. That was great. As you were speaking, well, maybe while I say this, Anthony, if you could pull up your presentation,
Yeah,
that'd be
sounds
great.
good.
Leah, as you were speaking, I was thinking about just fermentation and maybe, sauerkraut or kimchi and how humans are developing that and then maybe introducing that into other foods and then we can eat it later, right? So PHA being this fermented product that microbes are making, which are storing later, which they can blend into other foods to consume later. Yeah, really fascinating.
I
Thanks,
love
Leah.
it.
I know Anthony will have more food related examples here, but so excited that you're joining us. Anthony, a short introduction here. Um, he received his PhD in 2021 from the University of Houston in polymer chemistry, where he's working block copolymer synthesis, which bridge radical and insertion polymerization techniques. These block copolymers were utilized for the compatibilization of two or more polymers, and during that time, he served as BP for his local Society of Petroleum Engineers chapter, where he received several technical awards and recipient of a National Science Foundation Fellowship. He currently works as a senior formulations engineer and leads the development of new bio-based and compostable compounds under the Nature Tech division of NTIC. He serves as a member of the ASTM and participates as a member in the BPI Standards and Procedures Committee, where he provides insight into polymer chemistry properties and behavior, and it's excellent at explaining things that are fairly complicated. So thank you for presenting today, Anthony. The floor is yours.
Thanks for that introduction. And yeah, this is my second time, so I'm very excited to now switch from, I know last time we talked a lot about PLA and now we get to talk about PHA. Our company specializes in blends. So this is definitely, we're working with multiple polyesters, and I wanted to break that down for the audience here when we're talking about all these different kinds and what's so unique about this. For now, I want to start with what we typically would say are traditional plastics. A lot of you out there might see a lot of these recycling symbols, and you might see something that has the letter P followed by a variety of letters. Typically, this is like your polypropylenes, polyethylenes, polystyrenes. And last time I talked a lot about what is kind of the fundamental difference between traditional plastics and compostable plastics. So you can see here, I think of plastics a lot as these strong chains. And when we're talking about traditional ones, they have this carbon-carbon backbone polymer. And this is something that we would be, at least from a chemical perspective, they're very strong. They're hard to break down and attack. And you can imagine this is important when we're talking about compostability, biodegradability. So if we're focused on PLA, you can imagine that that's not the only polyester, obviously. We have PBAT, PCl, and of course, PHA. And the thing that's common between all of these polymers is that you can see that these don't have a traditional carbon-carbon backbone. These actually have a ester, which is why a lot of times you might hear these referred to as polyesters. If you look at the difference from the left and the right, it really is the backbone that's changing between these traditional plastics and compostable ones. Now, a lot of the times people will tell you that these are a family of polymers. So I might say that I have PLA and PHA. So even though the backbone might look similar, they do have very unique differences that you can capture in terms of products you can make, and also in terms of the differences in their performance. So PLA, I might consider, if I'm thinking of a family, I might say it's like a dog, and maybe for this instance, I'll call it a Chihuahua. And PHA, maybe I think of a husky. Now, the difference here is that even though these are both dogs, you can imagine that they would thrive in different environments. So maybe my Chihuahua would do well at a dog park, but it's not going to win an Iditarod race. And that's where you might see the difference when we're talking about, as we choose plastics, there's different environments in which they might actually excel or be utilized in. And the question today that I hope I can leave a lot of you with is, why do these perform so differently? Even though they're in the same class of polyesters, they have this unique backbone. What is different between all these polyesters? So in order to think of that, again, we're going back to this idea of biodegradation and compostability. And a lot of people tell you as a rule of thumb that some environments are considered easier to biodegrade and some are going to be considered harder to biodegrade. In fact, Leah touched on this a little bit when she described all the different certifications you can get. You can think of industrial composting. This is definitely something that most polyesters that are serving at least biodegradable and compostable solutions are trying to meet. Whereas if you go to home, you can imagine there's differences in temperature, there's differences in the environment itself, and all of this is going to change how plastics break down. So if we're in an industrial compost pile, you can imagine all four of these polymers we know are certified compostable when they go to an industrial facility. However, when I go to a home composting condition, you can see PLA is no longer meeting that biodegradability as a neat resin. And even as we continue down this path, you can see that certain polyesters can break down in these environments while others will not. And the question is, what is so different about, let's say, PLA and PHA? Why do they break down so differently in these environments? So a lot of scientists have done these studies where they would make plastic out of PLA and PHA and said, how do they break down and what is different about the way that this happens? So we'll take PLA, PHA, let's say that these are films that we made of the polymers. And we want to understand what's happening once it's in this compost pile. You can imagine over time, if I'm looking at this film, it doesn't look like anything's changing. Over time, PLA, and again, we know it's compostable, it's passed this test, and then eventually it will look like it just fragments and shatters and breaks down into all these small pieces. So it gets to this critical point where it explodes, and then eventually all of it has been consumed and it turns back to CO2. Now you might imagine PHA, there is some difference that we notice. So while PLA might be considered this bulk erosion, the entire piece is breaking down to a critical perspective, PHA is a little bit different. You can see here it looks like from the outside inwards that the PHA is being eaten, and it's just getting smaller and smaller until it finally goes away. And this is something we could consider surface erosion. So these differences in how the material actually breaks down in environments can help us understand why these polymers might be behaving differently. So the question is, why are they breaking down in these different ways? I'm going to focus on PLA real quickly. So you can imagine for PLA, in these compost environments, in these biodegradable environments, there are microbes. Microbes are, again, you can imagine how we eat food and turn that into CO2. That's the job of the microbe. We always want these polyesters to be converted back to CO2. Now, the question is, when will they actually recognize some of these polymers as food? So you can see here, I have my PLA chain, and maybe to the microbe, it's not very apparent what this is. And over time, something is happening where the actual chains of PLA are breaking down until it gets to a point, and you can see here, it went from a circle to something that looks like pizza now. At this point, the microbe will recognize that the PLA has broken down enough. It is going to be a suitable food source, and now the microbes can actually breathe that out as CO2. So if we're thinking of bulk erosion, some polyesters have to break down a little bit before microbes can utilize them. And again, a variety of factors can be at play here, but for PLA, just keep this in mind that something is happening over time. It's breaking down until the microbes can actually utilize this. So if we move over to something like PHA, and in PHA's case, again, we know that this is a surface erosion effect. I still have my hungry microbe. And this is one of the nice things that Leah mentioned. PHAs are made by microbes. So microbes instantly can recognize this as a food source. So the reason that they start eating it from outside and towards the center is that at all points, you can imagine it's like spaghetti. Even if I make the spaghetti chain longer, I can still eat it continuously. And this is what's happening with these microbes, the difference between a bulk erosion and a surface erosion. So if microbes can readily recognize something as a food source or not, we still have to go back to what's happening in these different environments then. You would imagine maybe if they break down enough, certain microbes should just be able to eat it eventually. So let's look back at industrial, home, soil. All of these will have different microbial populations. So an industrial compost pile, you're going to be at very high temperatures. So you can imagine the microbes present there are going to be different than the microbes present in a home compost pile. So maybe the microbes that are present in industrial composting, PLA breaks down really well and the microbes are able to utilize it. But you can imagine as we keep going through these different environments, the microbial population, even though they're always present, there's going to be a dominant species. Some microbes will thrive better at lower temperatures. Some will thrive better in marine or aqueous environments. So for a company like ours, where we do a lot of blending with twin screw extrusion, the question that we get asked a lot is, what happens when you take something like PLA and combine it with PHA? What is the value add that you can bring to someone when you know that they have different ways of breaking down? Can you somehow unify those and improve the properties of, let's say, PLA for its end of life? So home composting, and I know I said this in the beginning, PLA is not home compostable by itself. And we know PHA is. And one of the questions is, if we combine these two, can we force microbes to actually see this blend as something that is home compostable? So if I'm a microbe you can imagine I'm in the compost pile, and there's a lot of different places I could go in order to, again, these are food to them. They can be eaten, they turn into CO2. So it's just like driving down the highway. As you're going by, each of these signs might pop up, and maybe you'll see a sign for Papa Luigi's antipasta. We'll call it PLA for short. And you'll see here that if the microbes see that sign, they might say, no, that's not something that I want to eat. It's not even recognized as a food source. They see Papa Henry's, however, and they're like, PHA, that's something I can go ahead and eat. And the nice thing about these blends, especially for groups like ours, where you're trying to really balance the chemistry of not only the properties, but the end of life, is when you take these two together, microbes can actually consider blends of PLA and PHA, and they can meet home compostability. And this is where a lot of that impact that PHA has, not only as a neat resin, but it can be used in these blends. So I would say the takeaway for today definitely is that PHA alone, of course, can meet all of these different environments. But if you want to expand the end-of-life options for other existing plastics, you can also think about taking them together, blending them, and understanding that there are new opportunities out there as well. And I will stop right there.
Thanks so much, Anthony. Yeah, it was great to continue the explanations with food. I know you said a lot when you talk about composting, and I feel like in our bioeconomy conversations, as we continue to work towards that, it's just we're just working with nature, and nature creates, consumes, just like us. I would like to make two quick announcements. If you have any questions, please use the Q&A chat box. I don't see any questions right now, so feel free to open them up. Be the first one, and our presenters can begin to answer them in writing, or we can do it live after Michael's presentation. And then the second one too, if you have an AI note taker, BPI does not allow them in meetings or in webinars, so we just ask you to please stop them. I don't know how to do that. We don't know how to do that in some instances, so please, if you could do that, that'd be great. So our last speaker before the Q&A is Michael Adams, and we're excited to have him here today. He's a senior manager and sales executive and general manager with more than 30 years of experience building brands and driving growth across highly competitive industries. His career spans Fortune 100 companies, including PepsiCo, Kraft Heinz, and Georgia Pacific, as well as sports organizations and sustainability-focused manufacturers. He serves as VP of Innovation, Sustainability, and Marketing for WinCup, where Michael works with governments at all levels on legislative initiatives. His focus is ensuring that emerging biopolymer technologies are understood and that policy supports technological solutions to the plastics pollution crisis. He's a graduate of the Wharton School at the University of Pennsylvania, and we're excited that you're here with us today, Michael.
Great. Thank you, Jorge. I appreciate it. Thank you both to Leah and Anthony. It's fun giving this presentation while having some experts do a lot of the scientific heavy lifting. It takes a little pressure off of me. So anyway, it's a pleasure meeting everyone on the call today. If I don't or haven't had the chance to meet you, it's a pleasure. And for those familiar names and faces, it's good to see you all again. I'm going to go fairly quickly through a high-level story of our journey as WinCup into this great new technology, how it all started, where we're at currently, where we're headed into the future. With that being said, this is a shot that really defined an innovation turning point for our company. This is a snippet from a video that went viral. If you look in the lower left-hand corner, you'll see this has been viewed over 116 million times. It's a snippet of a sea turtle that was rescued off of the coast of Costa Rica by scientists from Texas A&M University in late 2017. As you can see, this turtle had a drinking straw embedded in its nose. And this was a turning point. It became viral at 119 million views. Obviously, that speaks to virality, and it changed our global community. It inspired numerous NGOs to really drive bans on plastic drinking straws. It created a movement at the community level to ban drinking straws or to shape legislation and policy to block certain items from going into marketplaces. And for us as a company, we literally got phone calls from every one of our customers asking us what were we going to do. It was a turning point moment. And we explored a number of different options as a company. And every time the after the equal sign came back to one thing, which is there's got to be something new that we can lean on to drive to the next level. And we found a material called polyhydroxyalkanoate in 2018. And while we were told we couldn't do anything with it, we said, let us be the judge of that. We worked on 28 different trials. The first one nearly burnt down one of our 8 manufacturing facilities. But at the end of the day, in 2020, we created and launched a brand to go directly at the problem that you see defined in this photo. Plastic proliferation continues to be a problem. And whether you look at the study put out by the Ellen MacArthur Foundation back in about 2018, or more recent studies, what you find is that recycling as a stream for plastics continues to be less and less reliable. It's not saying that it doesn't work. It's saying that more and more and more plastics societally are not entering into recycling streams. And so while we as a company, and I think this community globally supports the 3 R's, reduce, reuse, and recycle in terms of plastics, that phrase isn't solving for the problem. And the sad reality is really the last bullet in the upper section. Consumers are really starting to lose trust in the traditional waste streams. They're losing trust in recycling, and they're really not sure what's happening. Some consumers now have full doubt. Others still believe and want to believe that recycling is working. And in some markets, that is probably true. But we have a real problem. And so as a company, as we developed this PHA technology, one of the solve fors was, for us, we became champions of the 4th R, and we call it simply replace. That we need to focus on replacing traditional fossil fuel-based plastics with biopolymers that can meet the performance standard of customers and consumers around the world, but bring far significant consumer benefits. You know, it's interesting, I talk about this frustration, but last year at the BPI Summit, many of you probably heard Suzanne Shelton gave a phenomenal presentation that really kind of focused on the mindset of the consumer at this moment in time. And one of the quotes that I walked away from was a very simple one, but it's the last one on this slide, which is, why can't manufacturers just make products that go away? And I think PHA is that turning point moment that enables for a lot of that. You've seen this slide. Leah covered it. I think Anthony covered it as well. I'm not going to spend too much time on it. You've certainly seen the left-hand side. Leah covered a lot of this, and you'll see, you know, that graphic in the lower left-hand corner, which shows bacteria and the fatty acids inside of it, which is what PHA is. But on the right-hand side, from a converting and manufacturing perspective, I'll talk briefly. What we are provided by the manufacturers of the resin is a series of beads that you see in the lower right-hand corner. And we take that and do what we need to do in terms of melting, extruding, thermoforming, or injection molding that into products that can be used by consumers and customers around the world. And you can kind of see how it flows. And the beauty is through biodegradation, the circularity of the process continues, depending on how the product is broken down. If broken down aerobically, we see that the CO2 becomes fuel for plants with the sun to grow and create that circular environment. So FADE was created and launched in the summer of 2020 in the middle of a pandemic. And it was never WinCup's intention to create a brand of straws. It was always our intention to use a straw as the foundation point for a portfolio of products that can truly drive and emphasize sustainability, compostability, and biodegradability. In the 5.5, almost 6 years now, We're proud to say that we've sold over 5 billion drinking straws in that short period of time. I'm a geek about going to the moon, so it takes 2 billion straws, 7.75 inch end to end to get from Earth to the moon. So at 5 billion, we've gone to the moon, come fully back, splashed down, and launched again. So very exciting for us, and we continue to push and grow as part of a global community that is continuing to push more and more PHA in the drinking straw category. But we were very excited in 2025 to take this technology and parlay it into disposable cutlery, which is certified as home compostable as well as industrially compostable, only because of the size and the mass of the pieces. It meets the time criterion in those environments. It goes to exactly what Anthony was talking about in his presentation, as well as drinking cups. And as we like to proudly say, we're one of the first to enable a paper drinking cup to actually be a paper drinking cup, not lined with polyethylene, but lined with a material that will help that cup return to Earth in a short period of time. Pictures are great and always show nice proof of what PHAs can actually do. These are photos from OWS, which is the certified lab we use for all of our testing and certification. And you can see this was for a home composting certification done, but by week 9, you can see the materials were released. But one of the things that's so interesting, and it gets again to both Leah and Anthony's presentation, is the different types of environments that PHAs are able to biodegrade in and show disintegration in. And one of those is a marine environment. And instead of just showing photos, we as a company decided it would be highly impactful to show a time-lapse video of our products breaking down in a marine environment, because that impact would be significant. And so I'm going to close out today with showing you what that looks like, and hopefully it'll leave a lasting impression. I can tell you that I fell out of my chair about 100 times over watching that video when it first happened. It was pretty amazing to actually see the power of this biopolymer. Last slide I will close with something that we're very proud of. Obviously, in the spirit of the World Cup, we're thrilled that the nations of the world are coming here to the United States as our guests. We're thrilled to host them. Many of you in your communities are hopefully able to interact with these our global friends. We're thrilled and proud to be part of a larger community. Certainly, we know many of the venues are using eco-friendly and or biodegradable products in their venues. But we're thrilled to be able to say that 5 of the 16 venues in the World Cup are currently using fade straws, and it's something we're incredibly proud of and humbled by. We would love it to be an even bigger number, candidly, but again, we're thrilled at that. And so that's a little bit about us and WinCup. And hopefully, if you're able to attend a match, please, in one of these buildings, please look out for and enjoy using a fade straw. That's all I have. Thank you.
It's great. Thank you so much, Michael. Thanks for showing that video as well. I was waiting to watch it live during this webinar, so it's really impressive. Thank you all so much for presenting. We're going to be wrapping up the formal recording right now and then opening up the Q&A. I do want to leave the audience here, which is on the recorded portion, with an invitation to go to the BPI website and look for the webinars, and also to the YouTube channel and search the webinars and other great content that BPI is putting out there, of interviews with a lot of the practitioners, including this one, which will be up live soon, to learn more. So thank you all, and now we're going to switch over to the Q&A portion